What I'm going to talk about is why we're interested in ice cores, so why ice cores are such a useful geological material and how they work. Some examples of ice core data sets that have made a difference, not all of them produced by me, I should hasten to add. And then I'll move on to interglacials, what they look like, how we get into one, how long they are, and then some future ideas. So first thing to do is to show you what an ice core looks like, and I always do this at the beginning of my talks, because now twice, I normally say once, but it happened to me a second time a couple of months ago. I've given a talk, and at the end of it, someone has said, now about these icicles. So I obviously have, firstly, I have very bad diction, but secondly, I want to show you what an ice core looks like. So typically a cylinder of ice, 10 centimeters diameter, a couple of meters long each time. So when I talk about a 3,000 meter ice core, that's 1,500 times up and down the hole. So that's what an ice core looks like. And also, just to give you the impression that however eminent one gets, and on the day you get a medal you start to feel eminent, you still have to get cold and do some work. There in the corner there is me analysing an ice core somewhere inside that suit, actually in Antarctica. So ice cores are one of a number of sediments that we use to look at the relatively recent past, or sediments, a number of stratigraphic materials, I think I should say, such as tree rings, marine sediments, lake sediments, and so on, and they've all got their pluses and minuses. So the pluses of ice cores are that they're well dated, not as well dated as tree rings, I would never claim, but almost as well dated as tree rings at some sites, but unfortunately not at the ones where you get 800,000 years. There you can't count them every year. So they're quite well dated, but not as good as you sometimes imagine. They go back 800,000 years, that's a long time for me. Okay. First cores I drilled were only 20 years long, and I thought, 100 was great. 120,000 years in Greenland. They're atmospheric signals. The atmosphere's, I know we all do a lot on the ocean, but the atmosphere is quite important. Most of us live in it. So knowing what's in the atmosphere is quite important. And you get a lot of variables on the same core. So the greenhouse gases, something about solar forcing, something about volcanism. So all those forcing factors, all in the same core as a climate record. The negative bit of ice cores is really their location, although you can get ice cores from the tropics if you go to very high altitudes. They're extremely hard to interpret. As an example, the water isotopes that tell us about temperature don't tell you about temperature in the tropics, they tell you about the amount of precipitation. So the ice cores we can actually use for climate work are geographically limited to the poles, and even I have to admit as a polar scientist that some of the action in climate science happens in the tropics. So ice cores by themselves won't tell us what's going on. My favourite map of the world because it highlights the right bits, just to show you where I tend to go, Greenland and Antarctica. And how does the ice core record work? Well, it's one of many sediments. The sediment is the ice and the things in the ice that come out of the atmosphere when the snow falls. The difference compared to most sediments is that the ice flows, and as a result the layers thin with depth exponentially. So if you want to get a lot of years, you really do have to get to the bottom, because 90% of your years are going to be in the bottom 50% of the core. And we tend to drill on domes. You'll see lots of domes mentioned, and the reason for that is that all the snow in that column fell as snow here, whereas if I go here and drill a vertical core, then the snow at the surface fell here, but the snow at the bottom fell somewhere. In Antarctica, that could be hundreds of kilometers away. So that's why we tend to drill at domes. The type of signals we've got in ice cores are firstly the temperature signal, the isotopic content of the water molecules themselves, the oxygen 18 and the deuterium, which is, so this is a short talk, so all I say is it's determined mainly by the temperature at the time of snowfall. There's an entire lecture, as I've told people many times before, on why that's true, and there's another entire lecture on why it's not really true. I did get caught out the last time I said that because somebody said, would you come and give that lecture? I've never actually written it, but there would be one also. Then there are all the soluble and insoluble impurities that are trapped at the surface by the falling snow, of which the most obvious example, the simplest example to explain is the volcanic one. Every time sulfur dioxide goes into the stratosphere, you end up with sulfuric acid falling out all over the world, including in Antarctica, and you'll see an increase by a factor of several after a big eruption, like Tambora, for example. You'll see an increase by a factor of several in the sulfate content of the ice falling out on the surface, And then finally, there's the very special part of ice, which is the air bubbles, which only close off at depth. It's just a porous medium down to, say, 70 or 100 meters. When those bubbles close off, they're like a container, and whatever's in them, which is all the stable gases in the atmosphere, will be a representation, in fact a sample of the air at the time, which, if dealt with carefully, is just as good a sample as if you went out and took a canister right here and measured the contents of it. Show you, there are the bubbles. What they look like, they're a few tenths of a millimetre across, just in cross section. So now we move on to, that's how they work. Now what have ice cores done for us? So there are three things I'm just going to highlight. The first, establish some facts about the recent past. If you actually go through an IPCC report, then you will find an awful lot of ice core data in there. You won't always realise it's ice core data you're looking at, because it might be a record of past volcanism or past solar activity or something like that, but it's a lot of ice core data about the recent past, and it provides a grounding for some of the things that we actually know in this contentious debate about climate. They've shown the dynamics of glacial interglacial cycles, and they've shown that rapid climate change has happened. So I'll go through each of those in turn very fast. So this is one of the facts about the recent past. This is carbon dioxide over the last 1,000 years. The blue line up there is measurements in the atmosphere. I've actually taken Mauna Loa here, which was the very first station to be set up, measuring CO2 continuously. But I could have put South Pole on there and it would look exactly the same. And then all the other data on there are from ice cores, from those bubbles I showed you in ice cores. They're actually from 4 different Antarctic ice cores. There's a 5th one just been added recently in the literature, which I haven't yet put on here. You can see several things on here. One, you can see when carbon dioxide rose out of its previous range. I won't say its natural range, because there are some people out of its standard range, about 1830, I would say. See how much it's risen, that's 40%. You can see that it did have some natural variability. You can just about see a little dip across here, which is present in all the records. And you can see that all the records pretty much agree with each other, which is encouraging that there aren't any artifacts in there, because they're from very different sites with different contents of other chemicals, for example. There is still a couple of parts per million uncertainty in there, I should say, from the different records. Now if we move to a completely different time scale, we'll go up to 800,000 years. This is the EPICA project that I mentioned in my response. And in particular, I'm going to talk about the core from here, Dome C, which is the oldest core drilled so far. There's one that rivals it at Dome Fuji here from the Japanese drilling, which is 700,000, but Dome C is 800,000. Move on. Okay, that's what the record looks like for climate over the temperature over the last 800,000 years. Now, I've been naughty here because this is really the deuterium record, and I've just put a temperature scale on it. You can rescale this temperature. Whoops! You can rescale this temperature scale slightly if you want. So what you've got here is a Holocene, the last 10,000 years of relative warmth. Last glacial period here, which was cold in Antarctica, as well as giving us ice sheets over Northern Europe. Last interglacial, which in Antarctica was somewhat warmer than today, and therefore represents a very interesting period. I'll talk about that in a minute. Previous glacial, and so on. So we've got 8 glacial cycles on here. Well, actually, that's one of the things that I want to say about interglacials. If I don't tell you there are 8 glacial cycles, you probably don't see 8 on there. Actually, you probably see about 10. And I probably won't come back to that, but I think that we have got ourselves slightly caught in our understanding of glacial cycles and what their timing is. And there's also the question of what CO2 does in that period. So this is the climate record, exactly the one you saw before, and here's the CO2 record at the same time. And at least from the distance you're probably looking at, they look very, very similar. Now, there are differences between them, and we can have a long talk about causation and which way round the sensitivity is working. Of course, it's working both ways round because it's a feedback, but they do look extremely similar, and this is consistent with our understanding of what's going on in glacial cycles. We think from mainly from modelling work, I have to say that CO2 is responsible for up to half of the glacial interglacial warming, and it's probably controlled through processes in the Southern Ocean, which are really just say that putting together the first thing I showed you and this one, that despite these big changes between glacial and interglacial in CO2, it's all been dwarfed compared to what's happened in the last 2 years, well outside the natural range, and we don't have an analogue in the ice core record, at least for this. So if you want to know about CO2 at an earlier time, when the third example I want to give is very rapid climate changes. This is Dansgaard and Oeschger of the Dansgaard-Oeschger events. For those of you who've heard them, that's Willy Dansgaard and Hans Oeschger. Easily have mentioned in my response as well. And what you see here is a Greenland temperature record going from 40,000 years ago to the present. And here you see these very rapid climate changes, actually vertical the way I've plotted them now, but they occur in roughly 40 years, 10 degrees in Greenland, a bit less in different in the southern hemisphere. And although these can't occur now because the conditions with ice going into the North Atlantic or with large volumes of fresh water going to the North Atlantic don't exist, they show you that dynamically it is possible to get these very large rapid changes, which are believed to be caused by changes in the Atlantic overturning and therefore heat transport in the ocean. Now, I think if we hadn't seen these, then when modelers suggested they could happen, we would just say, don't be so stupid, go away and rewrite your model. But because we've seen them, we actually know that the models aren't sensitive enough. In fact, they can't produce anything as fast as this. Okay, so now I'm on to interglacials. I think I'm still okay for time, so I can actually talk about them. So why are we so interested in interglacials? Well, they define one end member of the Quaternary climate system. They're the warm end member of the Quaternary, or at least the later half of the Quaternary. We're in an interglacial now, which makes it quite an interesting time. And there are warmer periods than now in the interglacial records, such as I showed you the last interglacial, which might be helpful in understanding the future, although we have to be very careful to understand in what way that warmth is an analogue for the future and in what way in certain ways, but it isn't in others. I think in a very real way, interglacials are important because we claim, or at least climatologists claim to some extent, to understand today's climate, because if you put all the forcings in, then you get a climate a bit like today's in a model. But on the other hand, we don't really understand it in a way at all, because we don't understand why we're in interglacial exactly now, why we're in interglacial now rather than 20. So actually this is quite fundamental to understanding today's climate. So it's actually worth looking at the last interglacial as an example of the last thing that I said about warmth. This is the deuterium record in Antarctica, so that's the temperature signal. This is the oxygen ice in Greenland going from 150,000 years to the present. Greenland only goes back 123,000, unfortunately. We're desperate to get it from Greenland, but haven't succeeded yet. You can see that at least at some point in the last interglacial, it was warmer than at any time during the Holocene in both polar regions, possibly not at the same time, because we don't have this bit yet. We don't know whether it was at the same time. I know that sea level was somewhere between 4 and 9 meters high. What I've actually done is to take the synthesis done by Koch, who said something like 6 to 9 meters, and some earlier papers that said 4 to 6 meters, and put them together because I judged I'd go 4 to 9 meters higher. The question is, what was the climate that drove a sea level that high, which means that you've got to lose either the Greenland ice sheet or the West Antarctic ice sheet, and at the high end both. So we really want to relate this climate to this sea level. Crucial to our climate over the next, not over the next 100 years, but over the next few thousand. So interglacials are seen everywhere, not just in the poles, of course. They're a global phenomenon. I put a terrestrial, a marine, and an ice core record here to show the pattern of interglacials over the last 800,000 years, the ice core era. And I started off thinking that 20 years ago, I started thinking what we were trying to do was to understand a typical glacial interglacial cycle. How do we get in this sawtooth into an interglacial, how do we get out of it again? And it's actually, even when you look at just one site, Antarctica here, and look at the interglacials, you realise that's not what you're trying to do. You're trying to understand a much more complex pattern. So if I just take a few of these interglacials, and look at them, look at this zoo of interglacials, as I like to call them, then what we've got here is we've got short ones, we've got some tall ones, we've got a fat one here, and we've got a pretty thin one there, and we've got ones that slope up and then come rapidly down, and we've got ones that go rapidly up. We've actually got pretty much every behaviour you could have, and we won't be able to explain a canonical interglacial. Rather, we need to understand the forcing that led to each one of them. And there's also, of course, the question of what type of interglacial the Holocene is, and that's actually pretty tricky. We have written in the Epica paper that Brian referred to, we did write about this based on the way we saw it looking like stage 11, which is the closest orbital analogue we had at the time we wrote the paper. And so if you look at stage 11, you can see that it does look very similar to stage 11. It goes up, it comes down, and then it's sort of flat on the top. And so it looks as though it was about to be a long interglacial with a warm peak. But then after we wrote that paper, we analysed the rest of the core, which hadn't yet come back to the UK, and got to stage 19 over here, which is the next one that orbitally is very similar to the Holocene. And you can see stage 19 is over here. You can see up, and then it comes down, and oh, it was about to finish. So we've got two analogues there, which give you a different answer to this. So actually, we haven't got very far with using these as analogues, I'm afraid. Do we understand glacial and interglacial cycles? Well, in one sense, we understand them very well. That's to say, if you take a model, and this is a very simple model, the Gini-EMIC, intermediate complexity model, with a climate sensitivity that's pretty similar to the one that people think is central to the range of climate sensitivities, and you tell it what happened to the orbital insulation, to the carbon dioxide, and to the ice sheet extent, then you get the red line, the blue line, sorry, the blue line here, and the grey underneath it is the actual Antarctic climate record. So the model says the Antarctic climate should be. And you can see it's pretty similar. There are some differences, actually, ironically, in the interglacial. It's pretty good. In other words, if we know the forcing, we do well, just as today. If we know the forcing, we do pretty well. But what we don't understand is why the CO2 and the ice sheets changed in the way they did. So the difficult question is yet to be fully solved. And we all think, I'm sure probably everyone in the room thinks that it's related to Milankovitch, including me. I want to emphasise, I'm not about to say that Milankovitch is wrong. But having said that, Milankovitch is right in the frequency domain. That's to say the frequencies you get out of ice core records as marine records are the same ones you get out of Milankovitch. But nonetheless, you have to accept that the record that's supposed to be driving the global temperature record, which is this one here, Northern Hemisphere summer insulation works, that's supposed to be driving the ice sheets, which in turn are supposed to be driving everything else, does not look tremendously like the record at the top, which is the. In particular, while I can well understand why an interglacial occurred here, where the green I'll tell you why it didn't occur there, where there's a stronger change in insulation. No hint that the system was even dreaming of going into an interglacial. So the problem is that actually we don't have a predictive theory yet, and if it's not a predictive theory, then it's not a complete theory. So, just to finish up with something about the length of an interglacial, which is determined by when it starts and when it ends, and this now takes me on to work I've been doing more recently. So when does it start? And I'm going to take you straight to the punchline and hope that that's enough to help you get there. What I put up here is an Antarctic climate record at the bottom, actually two Antarctic climate records overlaid on each other from the Greenland climate record with these rapid climate changes. Somewhere during the last 5 minutes I've swapped from time going from left to right, whichever way around it is, but I'm sure you've all spotted that. what do we have here? I'm going to look at the Antarctic record because that's where my focus is, and other people have looked at it the other way around, but I think it's more helpful. So Antarctica started to warm, but then it stopped warming. And why did it stop warming? Well, I don't know why it stopped warming, but what happened was that Greenland suddenly jumped in temperature. So we would guess that's the overturning circulation switching on to its strong mode. But it doesn't actually matter what it is. Whatever it is, whatever a Danskar-Oeschger event is occurred, an Antarctic temperature turned over. It started to warm again, and then something happened in Greenland, manifested in Greenland, something happened in the ocean, manifested in Greenland, and it turned over again, and so on several times. And then there was a long period when nothing much happened, and then finally it started to warm again. It actually looks very similar to these warmings, and that's what we wrote the paper about, that it does look very similar to these warmings, except this time nothing happened in Greenland. Here, by which time CO2 was already so high that we were committed to it. So the idea of this is that what a termination actually may be is a millennial scale event just like these ones, which are normally controlled by the ocean circulation doing something that's manifested in Greenland, but at the termination, the control mechanism for some reason something to do with the size of the ice sheet, we don't know quite. This is a very simple idea actually that a lot of people were probably having at exactly the same moment because it was becoming obvious from the data, recently being very substantiated by a recent paper in what's going on, that you really do need these millennial scale events to kick you towards a glacial and actually constantly trying to, towards an interglacial system. The system appears to be constant. In this way of looking at it, the question doesn't become why do we get into an interglacial, but what stops us from going into an interglacial most of the time? What is it that stops us? That's the beginning of an interglacial. When does it start? Which now translates as what determines when southern warming finds itself able to complete. So then the other end is how long does an interglacial last for? And the traditional view would be that what you're waiting for is low northern hemisphere summer, which would therefore be roughly half a precession cycle after the termination. But if you actually look at the record, and here we've got both the deuterium and the CO2, you can see even from this 800,000 year plot that they're not all half a precession cycle long. Some of them are, but some of them are clearly 1.5 precession cycles, and actually there are a couple. I'm working on at the moment, and again, I'm not going to have time to explain it at all. What I'm working on is trying to understand exactly why this is, and trying again to look at this zoo of information, not just from ice cores, but from other records as well, to understand what it is about some interglacials that means that they're long as opposed to others. And one of the observational things, it may not be an answer to what's happening, but if you look at, I put up CO2 here, actually it would apply if I put up the temperature record. The ones that are long, the CO2 is either flat or starts to increase after the termination. Whereas the ones that are short, the CO2 peaks often very high and then immediately drops down again and starts heading for the glacial. So actually within 1,000 years of the termination here, you knew that this was going to be a short interglacial. You already knew this was going to be a long interglacial, or at least that's how it looks. So myself and various other colleagues doing different this are still trying to work on this. One of the ideas that I personally have is that it may well be something to do with the beginning that's determining the length of the interglacial, and that may be determined by what happens during the termination. But I just want to say in the last couple of minutes something about future ice core research. As Brian said, I'm the chair of this organisation, International Partnerships in Ice Core Science, which is very international. We've defined 4 big projects that we really want to see done, and 3 of them are underway. The bottom 3 are all underway. The top one is the most ambitious and the one that I hope will crown my career or something like that. And this now takes me to a slightly longer time period. We're not going to get much longer, but I'm at least going to give you a context. So here's Cenozoic climate, the longer term cooling of the Cenozoic. If we just focus on, sorry, I only gave you a very brief glimpse of a long time period. If we just focus on the last 5 million years, we know about this isotope record that leads us into a period when we have northern hemisphere glaciations. And if we just focus on the very last bit, 1.5 million years, then the ice core record so far covers just this period here, where we have roughly 100,000 year periodicity. I know that I made the point that it's not always 100,000 years, but still, if you do frequency analysis on it, that's what drops out. Back here, as most of you know, the periodicity is very clearly 40,000 years, which is a different facet of the orbital cycles. It's actually the tilt. And the whole community, would really like to know why that change occurred from the 40,000. We're pretty convinced we can find somewhere in Antarctica where we can get back, well, at least this far, maybe this far. And that's because on the rather feeble grounds, I have to admit, that when we drilled it to 800,000 years, we didn't choose it to be the oldest place, so there must be somewhere. But we're pretty sure there is somewhere, but it's very hard to work out where, to the extent that you're willing to tell a funding agency that you want millions of euros or dollars to do it. So we're working on that, and we're still going to be working on it, I think, for some years to come through geophysical methods to work out exactly where to drill in order to get back that. If we can, we'll immediately be able to refute or perhaps support one of the key ideas, which is that what's happening here was that the net during this period, allowing ice of them to become much longer, growing them to become much longer. From boron isotopes, real measurement of CO2, if I can say that, because we are actually measuring CO2 in the. So in summary, ice cores are a great archive of our past, and I'm very privileged to work on them, and that's probably only because ice cores exist that I'm able to stand here. They've given us various things we really wanted to know that give a factual, physical standing to some of the questions in climate science. On glacial interglacial cycles, although they've been studied so much by some very brilliant people over the last 40 years or more, there's still a lot to be done to really understand the pacing, timing and strength. But ice cores are showing us a lot about how the Earth works. They're needed for future prediction, and I hope they're going to carry on in this hall and elsewhere in the future.